Hi, so welcome to section 4.4, the real zeros of a polynomial function. Well, really, what we're checking, hi Maleficent, is we're checking the relationship between the real zeros and what we already know about like vectors and whatnot, especially with the remainder theorem. So what we did last time, unfortunately I don't have to write much because Mill's in the way. What we did last time, we did synthetic and long division. I wanted to show you that for both of these problems, whether we did synthetic division or long division, both of them are getting the same value, aren't we? So both times we're getting x squared plus 2 with a remainder of 1 over x minus 2. So much so, like, now, whatever. Now, here's what's really exciting. What I did on my graphing calculator, please don't bite me, Mel, is I put in the 0 of that factor. So we had the factor of x minus 2. I made it a 0, and I just plugged it into all those little x values. And watch what happens when I evaluate that. Please don't break. I get 1. I get the remainder. So by just plugging the 0 into the function, into the polynomial, we're able to actually find the remainder. Oh, that's cool. So that is our remainder theorem. A polynomial p of x is divided by x minus a. We can take that a value and we can plug it into the polynomial, and that tells us the remainder. So note that some people think that they are trying to find this remainder in two ways. They try to use synthetic and long division. No, we're going to use this remainder theorem in order to see those two different options. So if I wanted to find, I'm really scared to touch the screen because that's always when it crashes. So if I wanted to find this remainder by synthetic division, I could, I could just plug in p of 2. So what is p of negative 2? I get negative 2 cubed minus negative 2 times negative 2 squared plus 2 times negative 2 minus 3. So let's see, that's negative 8. That is also negative 8. This is negative 4. And this is minus 3. So let's see. So that's negative 8 minus 8. That's negative 16 minus 4. That's negative 20. It's negative 23. Alternatively, I can do that using synthetic division. So I grab the 0, or the number that I'm testing, and hopefully I should get a remainder of negative 23 when I do this. So I grab the coefficients, 1, negative 2, 2, and 3, drop it, 1, negative 2, that's negative 4, this is 8, that's 10, this is negative 20. Oops, I missed a negative there. Check it out. Negative 23. They both got the same thing. By synthetic division, I found the remainder, negative 23. And I could just find that by plugging it into the polynomial. Both of them, it's the same way to get the same answer. Is there a remainder? Yeah, it's negative 23. You can do it with synthetic division, like actually dividing, or I can just plug in the value and it tells me what the remainder is. Neat. All right, so the factor theorem is the same as the remainder theorem, but it's actually applying it to actually finding a factor. Because remainders are neat, but usually we're disappointed if we get a remainder. We want things to divide nicely. So the factor theorem is saying, hey, if you plug in that value and it spits out 0, guess what? You've got a nice 0, and that is a factor of the polynomial. So I want to determine if x plus 2 is a factor. So I can check that if it is a factor by plugging in that negative 2. I want to plug in the maybe 0. I don't want to plug in the factor. I want to plug in the maybe 0. So I do negative 2 cubed minus 2 times negative 2 minus 5 times negative 2 plus 6. Okay, so that's negative 8 minus, oh, that should be squared. That's also negative 8 plus 10 plus 6. So negative 8 minus 8, that's negative 16. Plus 10 is negative 6. Plus 6 is 0. Oh, cool. So that is 0. So that is a good factor. So now it says factor p of x completely. All right, so let's do that. So I'm going to divide out that x plus 2. I'm going to use synthetic division in order to do that, because synthetic division is easy, and it's something that I can do right now. So why not? So drop the 1, we get -2, double checking my negatives and whatnot. Yep. Add these together, we get -4. So that is going to be 8. Add these together, we get +3 and then -6. And that's 0. Okay. So now my factors, the thing I took out was an x plus 2. And my remainder, well, what my quotient after dividing is x. I want to go down 1 from 3. So 2 minus 4x plus 3. Okay. Now it did want me to factor this thing completely, and that's a binomial. And I can factor binomials, gosh darn it. So I'm going to keep my x plus 2, but that trinomial, I'm going to factor into 2 binomials. It's going to be x minus 3, x minus 1. Right? Yeah. Cool. I factored it completely. Hey, nice. Let me try another one. So for this one, I'm given a couple real zeros, and I want to try to find all of the others. So and I want to write my answer as a product of linear factors. So in order to find that, I'm going to do what I was just doing before. Like I could plug these things in. By the way, we're done with the remainder theorem. I know these are going to be remainders. They already told me that they're zero, so I don't have to check anything else. I'm just going to practice that dividing out. I want to give you lots of examples of doing all this. So I'm going to divide out a 0 of 1. My coefficients are 1. I don't have a cube, so I'm going to put a 0, a -5, a 10, and a -6. So drop the 1, get 1, that's 1. Add these together, it's 1 and 1, that's -4. And then this is also -4. And then this is 6. 1 times 6 is 6. Add these together and I get a 0. So after my first factoring out, I've got x minus 1. And then I want to drop that 4 down 1. So it's going to be x cubed, because I have 1 less degree now that I divided out a linear. X cubed plus x squared minus 4x plus 6. Yeah. All right. I'm going to go one step further. I want to get rid of that -3 next. So I've got my 0 of -3. Grab my coefficients, 1, 1, -4, and 6 again. All right, here we go. So drop the 1. Get -3, and that's going to be -2. This is going to be 6. -4 plus 6 is 2. That's -6. And I got 0 again. It would be real embarrassing if I got through that and I ended up with not 0, because they just told me that they were zeros. So I better be getting zeros. Notice that I'm doing the opposite sign for these things as I factor them out, because factors have opposite signs from zeros. All right, so my remaining stuff, I just had a cubic and I just divided it by a linear, so this should be squared. So that's x squared minus 2x plus 2. So it's telling me to find all of my real zeros. But looking at this thing, x squared minus 2x plus 2, that doesn't have any real zeros to it. And one way I could check that is I can take a look at my graph. So hold on a second. So here's my graph that I made. If you can double check in here, I've got x squared plus minus 2x plus 2. So there's my function. I can see my 2 zeros that I did get, that -3 and 1. But I also notice man, that graph is not coming down anywhere this way and anywhere this way. So it doesn't seem like I have any more zeros. And one way that I can also kind of tell is also kind of like how it's behaving over here. See how it's kind of like freaking out a little bit, like nowhere near the x-axis, but just kind of like freaking out over here a little bit. That's the imaginary zeros coming into play. So this is how an imaginary zero might look, where the graph is kind of doing something weird. I've seen graphs do weirder stuff, but already I can look at that polynomial and say, that doesn't seem factorable. That graph doesn't look quite right. I've got imaginary zeros. So the question asked me to look for all the real zeros, and I found them all. They already gave them all to me. That thing that's left over is giving me imaginary roots, so I'm not going to do anything else to try to write it as linear factors. Next time, though, we are going to talk about imaginary roots, and I'll go more in detail with that, but this video is long enough as is. So that's it for our real zeros today. Next time we'll be talking about imaginary zeros and some theorems. So yeah, thanks. Bye-bye.